My name is Michael Peters. I'm a principal engineer in emerging tech in Red Hat. Emerging tech is the part of Red Hat that tries to see what's coming in the future. So this talk is going to be a little bit different than what we've had before. We've had lots of talks about the existing capabilities of all these powerful systems. Some talks about sort of the future of some things, but this is really looking forward into the future. And I'm hoping to shift a little bit of perspective of how we think about identity, particularly software identity. But emerging tech in Red Hat, this is the group that brought you SigStore. That came out of our group. We brought Microshift, Kepler, Keylime, a bunch of other stuff that have made its way into Red Hat products. This is talking about something that isn't yet in a product. It's something I'm working on and that I'm really excited about, and I think others are too, but we'll get, and hopefully can get you guys excited about it. So talking about zero trust, first off, how many people have heard of zero trust? All right, yeah, it's a big industry buzzword. And it's not really zero trust. That's kind of a misnomer. It's zero implicit trust. But ZT makes a much better acronym. So instead of us walking around talking about zits all the time. So, but the implicit part is the key here, meaning that all interactions are verified. All interactions have an identity associated with them, and that identity has to be authenticated and authorized. And we apply zero trust principles to lots of parts of the application, networking, the data center, but here we're talking about the identity, and in particular, workload identity. So we're not talking about people, we're talking about automated systems, software identity. How do we identify software? So before zero trust, we had more of a castle and moat system is what we call it. So you have a data center that you're protecting or an application, and you have a firewall that's protecting everything. That's the castle part, and you have an entrance that would be a VPN or maybe some connections between a couple of different castles. But once you're inside the castle, it was assumed you're fine. You can access the things you need. And we know this has all kinds of problems, and including as we, things get more and more complicated, more and more systems, more and more attack surfaces. The old security paradigms of mapping everything to IP and ports and just trying to restrict on that doesn't really work. So zero trust reduces the attack surfaces in a couple of different ways. One, by reducing some of the shared secrets that are around, by removing open communication, right? In zero trust, everything is encrypted everywhere. So data in transit and at rest is encrypted, all communications encrypted, and we're trying to not have single points of failures like a VPN. So before we dive really deep into identity, because identity is a complicated thing, I wanted to ask a question. Why do we have passwords? Who can give me an idea for why we have passwords? They were kind of the least common denominator to implement some stuff, but why? Yes? Say again? To authenticate that you are that user, right. So passwords exist to assert an identity, right? And then because of that we can say, all right, we're guessing because you have this password that should be associated with this user, you are that user, and that user would have the rights to do certain things. Another reason we have passwords is to sort of assert trustworthiness. If software can present some sort of shared key, a secret, a password, something like that, we can try to infer it's trustworthy, right? That it was given that secret by something, some other part of the system, and we're using that as sort of an approximation of trust. But they don't, passwords themselves aren't necessary. It's what they represent. They're trying to represent identity and trying to represent trust. But passwords have a ton of problems. They get leaked all the time. They can be brute forced. We have phishing attacks that can get them. Lots of problems with passwords. And in an old castle and moat system, if identity existed, it was tied to a password or key. But it meant that multiple logically distinct workloads could be using the same password. And how many people here have tried rotating passwords or keys? How many have done it successfully without an outage or hiccup? Yeah, maybe kind of, yeah. It's hard. And if you do it wrong, you can bring down your whole system, which is just as the same as if somebody had attacked you. So we also have problems with how does your workload get access to these secrets in the first place? How do we apply identities and secrets to ephemeral workloads, to pipelines, build pipelines, serverless functions, things like that? So solving this identity crisis is crucial for zero trust. And I think a better way we can approach this is something called ambient credentials, which I'll talk about a little bit more later. But ambient credentials, instead of saying we're giving some secret to a workload and that establishes identity and trust, instead we establish the identity first and then trust it because we've proven the identity. And then the credentials are just part of that workload's existence. So we'll explain how that works in a bit. Mainly, talking about the project SPIFFE. How many people have heard of SPIFFE? All right, so SPIFFE stands for the Secure Production Identity Framework for Everyone. It was a multi-organization collaboration trying to distill all these many years of knowledge about how authorization and authentication systems work down into a single framework. It uses X509 certificates, which are the same certificates that are used in TLS and SSL connections. It can fall back to JWT tokens if you need to, if you can't use a full cert, but mainly you want to use a full cert. And it tries to solve what we call the bottom turtle problem. So if you've ever heard the phrase like it's turtles all the way down, well, right, there's got to be something at the bottom. And so when we're talking about a shared secret, how do you protect a secret? Well, let's encrypt it. All right, let's encrypt it. So where do we put that encryption key? I know, let's encrypt that, right? So and you keep going down, and eventually you have to come to something that you trust. And we call this a root of trust. So in SPIFFE, well, there's always a root of trust somewhere. Even if you haven't specifically designed it, there's one in your system. And if you don't know what it is, you're probably in trouble because you don't know where the foundation can break. And with SPIFFE, the root of trust isn't some ultimate super secret password, but it's the attestable identity of the workload and the machines that it's running on. So just a couple of quick SPIFFE concepts. The main thing we're going to be talking about is like the SPIFFE ID, which is an identifier that's given to a workload that uniquely identifies that workload. The SVID is this X509 certificate with the SPIFFE ID embedded into it. And then there's other parts of SPIFFE that deal with federation, how you deal with your CA, and you hook it up to that, and then how it communicates with the workloads itself. But we're just going to talk about those real quick. The SPIFFE ID, again, it's just a URL. According to the spec, it can be anything you want, but basically organizes how your workload fits into your organization. So in this case, a withholding routine running as part of the tax functions of the HR department for a specific domain. When we're talking in Kubernetes or OpenShift or something like that, it would have more restrictions on what that SPIFFE ID would normally, by default, look like. So something like the cluster name, the namespace, and the service account. And we can tie the identity into a service account. So if you reuse service accounts for multiple different things, they would all have the same identity. But this would be how a SPIFFE ID would work by default. So the Spire is the reference implementation of SPIFFE. Stands for the SPIFFE runtime environment. So a lot of times when you're talking, or you hear people talking about SPIFFE, they'll say SPIFFE Spire, or they'll say Spire when they mean SPIFFE, or SPIFFE when they mean Spire, but it's essentially SPIFFE is a spec, Spire is the implementation. And the spec can be implemented in various different ways, and in fact, parts of other systems that you might be using, like Istio, would have implementations of the SPIFFE spec. So Spire works by having an agent on each of the nodes, and we're trying to attest two things. One, the identity of the node that the load is running on, and the workload itself. And there's various different plugins that will work with the various different cloud environments you're using, that will work with Kubernetes, or just running on bare metal and Linux, that will associate to be able to assert whatever you're trying to assert about the node and about the workload. And so once they've attested this, there's this workload API that the workloads can talk to get their X509 cert, and then they can use that to assert their identity everywhere. And then Spire would take control over rotating the certs so that they're short-lived, and the workload has to periodically ask for that back. And that's all hidden under the Spire server and agent, and the workload just gets the credentials when it needs it. So this is what I was talking about with ambient credentials, right? There's no shared secret given to the workload. It's just that after we've proven the workload is who it says it is, and is running on a node that we say is what it says it is, then it's allowed to do things. And so with these credentials, this certificate, you can then let it talk to the various systems. You can integrate it with things like Istio, where that certificate becomes the basis of the TLS connection and other things like that. All right, shifting gears a little bit. Keylime is a project that I've been working on for a few years that came out of MIT and then was basically incubated inside of Red Hat's emerging tech team. It's now a CNCF project and was released in Red Hat as a product in Rel 9.1. But it's not the easiest thing to use right now because in order to really use it, you have to know a lot about your system. And to craft policy for it is not trivial because what Keylime does is it tries to use a TPM device on your machine, virtual or physical, preferably physical, and then the IMA Linux subsystem. And with those two things, it does what we call remote attestation. So it can monitor a fleet of machines. It can tell you if anything was modified on that machine that shouldn't have been modified. It can tell you, was the boot corrupted in any way? Are we running the kernel version that I specifically wanted? Were any kernel modules loaded that I don't approve of? All the way to saving these traces down into the hardware TPM, which allows you protection against things like rootkits and other attacks. Things that just a software monitoring system wouldn't be capable of because we have this hardware root of trust. Any changes made to the system are reflected in the hardware measurements and can be verified or cause a failure in attestation by Keylime. So Keylime makes sure that the declared state matches your actual state. Coming up with what your declared state is for your node, that's the non-trivial part. So let's bring these two together. What if we can leverage this hardware root of trust that does our boot integrity and our file integrity, and then make sure that that translates into our worker or our workload integrity? So we talked about Spire doing a node attestation on the machine that's running. Well, we can have a plugin, which is what I'm currently working on, that talks to Keylime to, one, verify is this node registered and following policy in Keylime, and then has it passed its attestation. So if the machine ever becomes corrupted, any workloads running on that machine would not be able to get their credentials. Which means that you can do some pretty amazing policy choices, and I'll bring those up in just a second. But so it works kind of like this. This is the Spire workload for getting attestations and just where the plugins fit in. So we have the Spire agent talking to the Keylime agent to verify who this node is, and then the Spire server talking to the Keylime verifier to verify that things have passed attestation. So this lets you craft policy like saying if this pod is running code that our application approved, meaning that it's the application image we select. If the machine hasn't been tampered with, then that pod automatically gets access to the database, or has an MTLS connection to other parts of the system. So instead of relying on some shared secret, we're actually using the attestable, cryptographically proven trustworthiness of the machine and the workload running on it. So, of course, this raises a lot of questions about how and where we define this policy, ACS, ACM, something else in Kubernetes, or in OpenShift, and then how all these things integrate together. These are all sort of open questions, but the desire to have this cryptographically proven, attestable identity of the machine, the workload, and then that provide the credentials. And then you just need to say, this application can access this resource if it's been proven to be okay. Any questions? It's kind of a whirlwind tour of some interesting new things coming along the way, but you should just be able to, hopefully, in the not too distant future, ditch passwords, ditch API keys, things like that for your internal communications. Yes? Yeah, I mean, IBM Cloud is using Keylime internally to verify all the nodes of their cloud so that no workloads can be run on, that customer workloads can't make it onto nodes that fail attestation. As far as like Red Hat customers, we're still working on that, but I do know there's some interesting stuff. There's a group in a university in Germany that's using Keylime for you bring your own devices for testing. So they can plug in a USB stick into any device they bring, and it can run basic attestation on that device to make sure it's compatible enough for their testing. So they can make sure that no one's bringing a hacked machine to pass their tests on or something like that. Yes? Between what? Oh, Kerberos and Spiffy? Kerberos is going to be like your integration with your Active Directory and other things like that, and it also deals with like person identity. Spiffy is just software identity. There's not like there could be integrations between the two, so that like the Spiffy IDs could be tracked somehow in your Active Directory or given groups and permissions that way. But as far as like establishing the identity, that's what Spiffy does. It's not about authorization, it's about identity. So we need to establish the identity of these software workloads running somewhere. Yes? Yes, we have been talking with like OpenShift, the new version of OpenShift Service Mesh that's coming, that's in developer preview. We've been talking with that team about how that's going to look when we do like ambient credentials on top of ambient service mesh. We don't exactly know the answer to those questions, but we are starting those discussions. It actually really excites me. Like, if you do it right, if the policy is crafted right, and in a lot of ways, like, because OpenShift is running on CoreOS, which we can know with a certainty what files are going to be on that system, we can say things like, if it's running this version of CoreOS, we know these exact files that should exist there. So Keylime can craft, or the Keylime operator for OpenShift can craft the policy automatically for those nodes. And if somebody tampers with those nodes, it would immediately fail attestation policy, and workloads would stop getting credentials on those. So integrations with OpenShift can exist that wouldn't exist necessarily in other systems. All right, thank you.